Good afternoon, ladies and gentlemen, students. We will start to today's I²CNER's international symposium series, and today we have very young and very active professors, and we expecting very interesting talk today. And today's talk title is Fundamental Studies on the Photocatalysis, and today's speaker is Professor Bunsho OHTANI from the Hokkaido University and Catalysis Research Centers. And as some of you knows him very well, he's very famous young researchers in this field, one of the pioneering works in this field. I would like to briefly introduce his personal careers. And he graduated the Kyoto University in 1981, I guess. And then he got a PhD from the Faculty of Engineering, Kyoto Universities. And from that time, he started to study on the photocatalyst. And then he joined to the Kyoto Universities after getting the PhD in 1985. And then he becomes, he promoted to the associate professor in 1996 and Graduate School of Science, Hokkaido Universities. And then he has some period to work with very famous Professor Uosaki in Hokkaido University. And then in 1998, he became full professors. And his current position is full professor in the Catalysis Research Centers, but he also teaches the Graduate School of Environmental Science in the Hokkaido Universities. And he has already published more than the 170 papers, and he's very high H factors. And then the 2005, he got the Scientific Achievement Award of the Electrochemical Society of Japan. And also 2006, he got the Japanese Photochemistry Association Award. So today we expecting the very interesting talk from Professor OHTANI. So thank you very much for visiting us, and we are expecting your nice talk.
Thank you very much, Professor Ishihara. But I'm not so young because my age is just the age of my father's retirement. So that is 55. So not so young. Good evening, ladies and gentlemen, the students. I'm very, very happy to be here. However, I have three pressures. One is I checked the list of lecturers in this seminar series, and I found that all the lecturers, except for me, are truly distinguished professors. But maybe I am a first exception of this category. And the second one is, for me, it is not so easy to speak English in front of Japanese audience. It is rather easy to speak English without any Japanese audiences, but it is impossible to avoid this. And the third one is that one, the camera. I forgot that I have accepted to be taken the movie, and that it should be will be uploaded to YouTube. But I remember last night, and I checked the homepage of the center and institute, and okay, so much pressure now. Okay, let me start my talk by introducing myself. Just introduced by Professor Ishihara. I studied in Kyoto University, and my graduate thesis is made by the supervision of Professor Kenichi Fukui. And however, he is a theoretical chemist and a Nobel Prize winner. But I was working in the field of a little bit different field, that is functional polymers. And this is a photo taken at the day of announcement of Nobel Prize in 1981. And this is the Professor Fukui's house. And this picture, this photo, was on the first page of Asahi newspaper on the next day. So my mother asked the newspaper company to send this photo to my house. Okay, and then in the Fukui's laboratory, the professor at that time he was associate professor Takeo Shimizu. He is a very, very famous polymer and supermolecular chemistry professor, and I did a master course study under the supervision of Professor Shimizu as the functional chemical functional polymers. And then I moved the laboratory to the Professor Kagiya's laboratory. He is a little bit strange professor, but I was very, very lucky because I changed my topic from the PhD course by the supervision of Professor Kagiya. He chose my PhD thesis topic to photocatalysis. This was my first experience to do such a study on catalysis or photocatalysis, and I was so lucky. So because he chose this topic, I am here. So that is very, very important point. And after getting the PhD degree, I worked as assistant professor in his laboratory. And then in 1996, that is 15 years ago, I moved to Hokkaido University and belonged to Professor Wasaki's laboratory. He is also not strange. He is a very, very characteristic person. And in Wasaki's laboratories, I changed a little bit the topic. That is the surface chirality. That is a little bit different from the photocatalysis. But that experience is very, very good for me. And after getting the full professor position in Catalysis Research Center, I restarted the photocatalysis study. And this is my notebook, and this is the first page of my laboratory notebook on the study of photocatalysis. And this is here is written in Japanese. That is mechanically mixed titanium oxide, ruthenium oxide, and platinum powder. That was used as a photocatalyst to produce hydrogen from aqueous 2-propanol solution. This is the first page, and that is 1981. So that means after then, I am working more than 30 years on photocatalysis. And this is my picture that is taken in 1984. That is my first experience of attending the international conference. And he is Professor Kyushu. He is also a famous professor in this field, and we discussed very much in this conference. And after 25 years later, we met again, and he is not changed. And I'm also not so changed. Okay, except for this part. And maybe the students don't know. This is a poster session. So this poster is hand-drawn. Okay, no copy machine, no word processor, just writing on this paper and different size of papers and just put. This is my first experience of presentation in international conference. And this is the topic is just photocatalytic synthesis of organic compounds. Today, I will not tell this topic. And this photo was taken maybe 2 years ago. And we have many students and foreign guests, and maybe you can find it. They are the postdocs and the PhD student from abroad. He is also the foreign student, and he was visiting us. And now the number of people in my laboratory is just 30. And very, very interesting point is just half is female. 15 females and 15 males. That is very, very extraordinary case in Japan. Okay, so let's move to my first topic. That is just introducing the heterogeneous photocatalysis. Maybe you know the name of photocatalysis. That has been already applied practically, and there are two important phenomena for the practical application of photocatalysis. One is the photocatalytic decomposition. The target is organic compounds, stains, or microorganisms, or viruses. So we can decompose those things by photocatalytic reaction. And also important phenomenon is the photo-induced superhydrophilicity. That is the surface covered with photocatalyst turns very, very hydrophilic. So we cannot see any droplet after photoirradiation on the photocatalyst-coated surface. And this is very, very good for making the washable surface. So by combining these two phenomena, the practical application of photocatalysis, there are so many practical applications of photocatalysis. One of the important application of photocatalysis is for tent materials. Maybe you know this name of this company, Taiyo Kogyo. This is the world, the #1 company for tent materials. And 1/3 or half of their product is just titanium oxide, photocatalyst-coated tent material. And the regular tent materials becomes very, very dirty after exposure in the ordinary temperature and ordinary atmosphere. And if the surface is coated with Teflon, fluorinated polymer, it is a little bit improved, but still there is some dirtiness here. But the coating of titanium on tent materials gives a very, very clean surface after exposure of 5 months. That is the organic compound, dust, or organic additives in PVC polyvinyl chloride of tent material is decomposed by photocatalytic reaction. And at the same time, the surface of this tent material becomes very, very hydrophilic. So sunshine decomposes the compounds, organic compounds or dust, and the waterfall washes out this dirtiness. So this is called self-cleaning. So without any additives, without any washings, just sunshine and waterfall gives the very, very clean surface. And this is our building. The central part of this building, we occupy, the Catalysis Research Center occupy the central part of this building. And this is the main entrance. And here is a very large window, glass window. And this surface is, you can see just a little bit refractive. So that is, the surface is coated with titanium oxide. That can be used for self-cleaning and also to reduce the radiation of infrared or visible light inside. And JFE, this is a very, very famous company. They produces such a exterior steel plate covered with titanium oxide. And we can expect the self-cleaning by using this coating of photocatalyst. And we can also be provided the paint material containing titanium oxide photocatalyst. And by painting the photocatalyst paint, there is almost no dirtiness here. And also here, this part is coated with titanium oxide photocatalyst paint. So you can see the color is a little bit lighter. So that means this part become dirty, but here this part is maintained very, very clean. And very, very famous building near Tokyo Station. Maybe you know the Marubiru. The window glasses of this building is just coated with titanium oxide photocatalyst to keep the surface clean. And some private company produces this type of partition, the wall, coated with titanium oxide to keep the surface clean and also decompose, for example, the smells or the compound included in this smoke of cigarettes or something, and that makes the surface clean. And also, very, very important application is for the mirror of automobiles. And this part is coated with photocatalyst, and this part is not. And in the rainy days, this part is not so hydrophilic, so there are so many drops of water. But here, this part is completely super hydrophilic. That means no droplets. So we can maintain the view of mirrors. And very, very challenging application is the road pavement is including the photocatalyst. That is the nitrogen oxide, NOx, is expected to be oxidized by the photoirradiation of the surface by sunlight to give nitrate, ion, as a result of oxidation of nitrogen oxide. And that is removed by, washed by rainwater. And you know there are so many writings in the tunnels, and this cover, the cover glass is coated with titanium oxide to keep the surface clean. Because of, since so many carbon from especially from diesel cars accumulated on the surface of glass, but it can be removed by light in this lighting system. And maybe you know this type of air conditioner or air purifier, including the photocatalytic devices. That is the small molecules. That is something kind of smells, ammonia, hydrogen sulfide or something. Those small molecules can be removed by photocatalyst. And this is also a very, very important application of photocatalysis. That is the photocatalytic reactor included in refrigerator. At first, that is the aim of incorporation of this photocatalytic device is to deodorization or decomposition, but of organic compounds for smells. But accidentally or after that, after introducing this device, people found that the ethylene, that is the signal compound emitted from vegetable or fruits that make the other vegetable or fruits to grow. So by decomposing the ethylene emitted from vegetables, that we can control the freshness of vegetable or fruits. And this technique is also applied to the container for the transportation. So to keep the freshness of vegetable or fruits by using photocatalytic devices. And okay, so in 2008, the total selling of photocatalytic materials is about 300 million US dollar, and almost half is for exterior materials, and this part, for example, air conditioner or air purifier is almost 1/4, and the others. Still, the market of photocatalytic application is still going up. Okay, again, I can say that there are two phenomena used in the photocatalytic applications. One is the decomposition of organic compound. This is the demonstration of decomposition of organic compound. This surface is coated by titanium oxide and stained by organic dye, methylene blue, and irradiated with photomask. And just below the photomask, there is no decomposition, but the other part is decomposed. And the other phenomenon is superhydrophilicity induced by photoirradiation. And the normal glass plate is rather hydrophobic, but irradiated photocatalytic coating gives a very, very high hydrophilicity. Okay, so maybe you can imagine what is the photocatalysis, and then I move to the mechanism of this reaction. This is the summary of mechanism of photocatalytic reaction, and this mechanism is generally accepted, and maybe almost all the people working in this field believe this mechanism. That is, here is the semiconducting material. The electronic structure composed of valence band, filled valence band, and forbidden band or band gap, and empty conduction band. And photo irradiation with light of wavelengths, light of energy larger than this band gap, excite the electron in valence band into conduction band, and at the same time, the positive hole remains in valence band. And this electron, the positive hole, is relaxed to the bottom of a conduction band and also to top of valence band respectively. And these electron and the positive hole react with compounds adsorbed on the surface to reduce them or oxidize them. Otherwise, they recombine each other to give heat, or in sometimes that is to give light. However, no chemical reaction occurs. So this is the generally accepted mechanism, and maybe it is possible to interpret almost all the results obtained in the experiments or actual practical applications. However, still there is a lot of questions in this reaction mechanism. One is, this is the band structure. So that means the electron in this band is delocalized. That is just the same as the HOMO or LUMO level, electronic level of usual molecules. For example, this is the benzene. The HOMO is just like this. This like this. And the LUMO is like this. And the transition from HOMO to LUMO occurs to give the excited state of a molecule. However, we don't say the position. Where is the excited electron? So just the transition between these two molecular orbitals. However, sometimes we say that here is a positive hole, here is electron. So this is just a localized state. So I think that at least after the photoexcitation, just after photoexcitation, the electron and positive hole must be delocalized. And however, after this excitation, this electron and positive hole may be trapped. And for the N-type semiconductor materials, there is a lot of electron defects. That is donor level for N-type semiconductor materials. That is the levels located just below the conduction level. And with the contact with water or electrolyte solution, this electron goes out and the empty level remains. And I think that such a electron deficiency may accept the photoexcited electron just after photoexcitation. So this is just before the photoirradiation. And photoirradiation produces excited state, and soon after the electron, trapped electron present. So this migrates to the surface to give chemical reaction. So this is my hypothesis, but nobody accepted this mechanism. But what I want to say is there must be a band structure and the photoexcitation happen. However, the important point is the state of after trapping. So trapped state must be measured and must be evaluated in order to predict the reactivity of electron or positive hole. So anyway, in the very, very first laser spectroscopy, we can find that the trapped electrons. And this is the one representative results of pump probe photoabsorption study of titanium oxide powder. And here is this point, the excitation occurs. And soon after, within 1 picosecond, we can observe the trapped electron. So we cannot see any free electron. Just the trapped electron can be found soon after the photoexcitation. And then this is reduced quickly, very quickly, but this part is very, very slow. So at present, we have no experimental proof for this mechanism, but we propose that this part will be due to the shallow traps that trap the photoexcited electron and releases very, very quickly. But this part is very, very deep trap that accept electron, but no migration, just waiting the recombination with positive hole. So now we are trying to find out the what kind of traps and how many traps are included in titanium oxide photocatalysis, and what is the correlation between these trap traps number or energy of traps with photocatalytic activity. So then let me move to the thermodynamics of photocatalysis. Maybe this institute is aiming at producing hydrogen from solar energy, and this is the photosynthesis, and that is just storing light energy in plants to chemical energy. And if photocatalytic reaction produces hydrogen and oxygen at the same time from water by using the photoexcited electron as a reductant and the positive hole as an oxidant, we can produce hydrogen and oxygen at the same time. This is very good, and this should be your artificial photosynthesis. And this trial to produce hydrogen and oxygen from water started from 1969 as a first report by Fujishima's Honda report. That is reported in the Japanese journal published by Chemical Society of Japan, that is Bulletin of Chemical Society of Japan. And 3 years later, that was reported again in Nature. And afterwards, there are a lot of electrochemical studies, but this list is just limited to photocatalysis, not using electrode system. In 1980, Professor Sato, he was working in our Catalysis Research Center, discovered the titanium oxide particle can decompose water into hydrogen and oxygen if the titanium oxide powder surface is coated with sodium hydroxide. And then soon after, the domain groups report that strontium titanate also decompose water. And afterwards, there were so many studies on photocatalysis of mixed metal oxides. And Domen and Inoue's groups very, very extensively studied this mixed oxide to produce hydrogen and oxygen under UV radiation. And in 1998, Professor Kudo's group reported the very, very highly efficient decomposition of water with quantum efficiency about 50% under UV radiation. But these are all under UV radiation. In 2001, Dr. Abe, at that time, he was working in ICE, but now he is working in my laboratory as an associate professor. He discovered the two-step visible light photolysis using the iodide mediator. That is the first example of complete decomposition of water into hydrogen and oxygen under visible light irradiation. And 3 years later, Professor Domen's group is a supervisor of this institute, evaluator. He discovered a one-step visible light photolysis by gallium nitride and ZeNO. So it is possible, but still the efficiency, quantum efficiency, and also the solar energy conversion efficiency, both of these efficiencies are very, very low, and almost below 1%. Something. And this is the example. This is the Domen's laboratory's experiment. The solid solution of gallium nitride and ZeNO produces hydrogen from water. And just I told you, there is a lot of application for catalysis, that is decomposition of organic compounds. And it is possible. And also decomposition of water into hydrogen and oxygen are also possible in photocatalytic reaction. So what is the difference of these two types of reactions? These two proceed by the same mechanism or different mechanism? The answer is the same. just the same. There is no difference in the mechanism of decomposition of organic compounds and the water photolysis. The same mechanism happened. That is the excitation of electron leaving the positive hole in valence band, and the electron is used for reduction, and the positive hole is used for oxidation. The same. So what's the difference? And why this kind of energy storing reaction occurs by photocatalytic reaction? That is very, very simple. If electron is photoexcited into conduction band, the half reaction, electron with something to produce oxidized product, a reduced product, this partial gives energy change is negative. And for the oxidation reaction, this partial gives energy change is negative. This is also the case for the energy consuming system. This is energy storing, this is energy consuming system. The overall product gives the delta G, positive delta G, and this is negative. This is a spontaneous reaction. But if we see this partial gives energy change, all these are negative delta G. That means it is possible to promote these reactions, even if the total overall gives energy change is positive. This is the how to say important point of photocatalysis. However, therefore, such kind of energy storing reaction can be promoted by photocatalysis. However, this is only when reaction by electron and reaction by positive hole proceed separately, independently. That is the very, very important point. So this reduction and oxidation steps must be separated spatially. So this is the important point. If that occurs at the same site or same place on the surface, the backward reaction may happen very, very easily because the overall delta G is positive. So it is necessary, at least it is necessary to divide these electron and positive hole reaction site. That is a very, very important point. So maybe you know the name of Honda-Fujishima effect. That is the first paper of photolysis of water. But not so many people know that the exact title of this paper. But I will show you the essence of this paper. That is, if the titanium oxide and platinum is connected with electrical bias and irradiation of UV irradiation to titanium oxide electrode produce oxygen at the titanium and hydrogen from platinum. And or this is short-circuited, but this part, titanium oxide part, is alkaline and the platinum part is in acidic media. The photoirradiation produces electricity, and at the same time oxygen and hydrogen evolution occurs. This is the content of the paper published by Honda and Fujishima in Nature. And the important point is electrical or chemical bias is necessary for production of hydrogen and oxygen at the same time. This is the title of that paper in Nature, the electrochemical photolysis of water. That is a little bit complicated words, but at that time, not so many relating work were done, so this is maybe chosen. And that is, there are some misreadings. One is the order of authors' names, not the Honda and Fujishima. We remember that the Honda-Fujishima effect, but the actual order of this author's name is Fujishima and Honda. And this is not so important, but this is not the origin of photocatalysis by titanium. So many papers cited this paper as the origin of autocatalysis, but there is no words. You can see any photocatalyst or photocatalysis you cannot see in this title, and also in the text there is no description of photocatalysis, and just the electrolysis. And in the strict bibliographic sense, this is not the origin of photocatalysis, but actually this paper promoted the study of photocatalysis very much. So this is actually the origin of studies of photocatalysis, but by bibliographic sense, this is not the origin. And the important point is they only suggest of water splitting by photoirradiated semiconductor materials. So there is no example of photocatalytic splitting, no example. And after almost 40 years, considering this, after 40 years, there is no progress, nothing. Very, very small in progress. For example, Domen's group or Professor Abe's study that produces hydrogen and oxygen at the same time, but very, very small efficiency. So there is no progress. So we have to learn from this paper. That is this hidden message here. That is requirement of bias potential. That is the electric field, because the electron and the positive hole have charges, negative and positive. So it is necessary to separate them by using electric field. So in the electrochemical, photoelectrochemical system using electrode, it is possible, very, very easy, by applying bias potential. But for particulate photocatalytic system, that is rather difficult. So I could provide the solution of this electric field problem, the charge separation problem, but I have no clear answer. But I can suggest that how we can produce such a system, particulate system, providing charge separation. That is the anisotropy of particle. That is, for example, we can produce such a decahedral anatase titanium oxide particles. This particle exposes two kinds of facets. One is 101, the other one is 001. Only two kinds of facets are exposing in this decahedral particles. So there should be some difference in the electronic energy between these two facets that may produce the electric field. Or this type of, how to say, macro, micro, I'm sorry, the two-phase structure. One is small micro scale structure and also the macro scale structure. So this kind of the anisotropy may produce such a field dividing the electron and the positive hole. Also, this type of quasar or this type of heterodimeric structure of different material may, I can say that just may provide the electric field dividing electron and positive hole. I'm sorry, just a suggestion for this. And okay, so in the last 15 minutes, I will show you the very, very fundamental studies, that is action spectrum analysis of photocatalysis. Again, I can tell you the mechanism of photocatalytic reaction in a different way. That is, photoabsorption produces electron and positive hole pair, And this is used for redox reaction, otherwise recombine to give no chemical reaction. So one of the important steps is how to improve the efficiency of utilization of once produced electron and positive hole. That is very important. So we discuss the quantum efficiency. That is the efficiency of using electron and positive hole to the actual chemical reaction. However, before this reaction, it is necessary for the catalyst to absorb light to produce electron and positive hole. So this step, photoabsorption, is very, very important, and this is the first step of this photocatalytic reactions. And what is the necessary conditions to prove that is photocatalytic reaction or not? That is, as a generally accepted necessary condition is reaction initiated by photoabsorption of photocatalysis. That is very, how to say, natural, or how to say, very, very simple. But generally accepted blank test for photocatalytic reaction is co-presence of three requisites. One is photoirradiation, one is photocatalyst or solid material, and the third one is the reaction substrate. Only in the co-presence of these three, if reaction occurs, that is photocatalytic reaction. So this is a generally accepted way of blank test. However, sometimes this is not the case. For example, if the compound, the molecule absorbed by the solid material absorb the light, and the photoexcited electron in the molecule is injected into solid material, and the electron injected molecule is decomposed. So in such case, the co-presence of photoirradiation and solid material and the reaction substrate, the co-presence is necessary. So we cannot distinguish these two kinds of mechanisms. So this is the dye-sensitized or sensitized mechanism. This is not a true photocatalytic reaction, because the material is, that is, the decomposed dye absorbed light, because that is, the reaction must be initiated by photoabsorption of photocatalyst. However, the dye, reaction substrate, absorb the light. So in this case, this is not a photocatalytic reaction. So, however, we can't distinguish. So the one possible solution is to analyze the action spectrum. So action spectrum is a spectrum of photo-induced reaction rate against the irradiated wavelengths. So by checking this action spectrum, we can check what kind of species absorb light to drive the overall photo-induced reaction. So maybe you know that titanium is a very, very easily obtained, very, very cheap material, but only absorb UV light. And it is necessary to improve this photoabsorption ability by some treatment, and the titanium becomes colored. So is it the visible light responsible titanium? No, maybe just absorb the visible light, but only by checking the color, it is impossible to prove that the photoirradiation of visible light drives photocatalytic reaction. So we need the measurement of photo action spectrum. This is the concept of action spectrum measurement. That is, the photoreaction or photocatalytic reaction is driven by the monochromatic light with different wavelengths, and the response that is the rate of reaction or product yield or current, if that is the photoelectrode. The apparent quantum efficiency, that is the efficiency based on the incident photons. The true quantum efficiency is measured, calculated based on absorbed photons. But in this apparent quantum efficiency, we use incident photons. And this is plotted against wavelengths. This is action spectrum. And therefore, this is the action, this is the action spectrum. And this is just a product of photoabsorption efficiency. This is a photoabsorption spectrum. And this is the quantum efficiency, wavelength dependence of quantum efficiency. If this quantum efficiency is constant, independent of wavelengths, the action spectrum, the shape of action spectrum is same as absorption spectrum. So by checking action spectrum, we can we know what kind of species, what is the absorption spectrum of photocatalyst. So we can, for example, we can discriminate the active crystalline phase in anatase and rutile mixture by using action spectrum analysis. And in the ordinary way, we have to use the monochronometer and choose one wavelength to irradiate. But this is not so time saving. So we introduced a new type of photoirradiation apparatus that is at the most 11 samples with different wavelengths can be irradiated at the same time. And we can obtain the action spectrum very, very easily. This is the representative results of action spectrum analysis. This dashed line is absorption spectrum, diffuse reflectance absorption spectrum of a famous titanium oxide, P25 titanium oxide, and just absorbing the light in the region of UV. And this one, this dashed line is for sulfur-doped titanium oxide. So by doping the sulfur into titanium, produces the visible light absorption here. And this squares is action spectrum by using these titanium oxide and the sulfur-doped titanium oxide for decomposition of methylene blue organic dye. And here is this part is almost the same as the absorption spectrum, but in this part, the very, very strange action spectrum is obtained. So expanded in this range, you can see the action spectrum like this. And there is no absorption of P25 or sulfur-doped titanium oxide in this wavelength region. So you can see this dashed line is the methylene blue adsorbed on the surface of solid. And maybe this action spectrum is made by the absorption of methylene blue on the surface, and that is decomposed after injection of electron into titanium oxide or sulfur-doped titanium oxide. So that is not a photocatalytic reaction. That is just a dye-sensitized reaction. So we can distinguish this type difference in those type of photoreaction by using this action spectrum analysis. And if we change the substrate into transparent material, in this case, acetic acid is used. Acetic acid cannot absorb the light in the range shown here. So by expanding this part, the sulfur-doped titanium oxide gives the activity in this region from 400 to 600 nanometer that coincide with absorption spectrum of sulfur-doped titanium. So by checking this action spectrum, the sulfur-doped titanium is really active in this visible light region. So that is very, very important to prove what kind of species absorb light to induce photo-induced reaction. That is the action spectrum analysis may be the essential technique to prove the photocatalysis. I have not so much time. Okay, this action spectrum study we reported in 2006. Before publication, we didn't expect the citation of this paper, because if someone uses methylene blue as a test compound, by reading this paper, they don't want to cite this paper because this is not appropriate for the test reaction. Use methylene blue as a test compound. So they never cite this paper. And if someone not using methylene blue as a substrate, they need not to cite this paper. So we couldn't expect the citation of this paper. But surprisingly, so many citations. So after the publication in 2006, more than 60 citations already. So that is very, very surprising. And we checked those papers citing this paper. And surprisingly, half of them used methylene blue as a test compound. And they didn't read this paper, just checking the title of this paper. And so this is our mistake to use such a question in this title. So is methylene blue an appropriate substrate for photocatalytic activity test? So we wanted to say that is inappropriate, but it is possible to consider this is okay. Methylene blue can be appropriate compound. So it is very difficult. Okay, that is very unbelievable situation, but we understand that such a number of citation doesn't make sense. Anyway, okay. In the last 3 minutes, I will show you the very clear example of titanium oxide. Maybe you know the P25. This is a code name of commercial titanium oxide. And this titanium oxide is very, very active in various type of reactions. And many people use this P25 titanium oxide as a de facto standard. And the important point is the P25 is composed of anatase, one of the crystalline phase of titanium oxide, and also the rutile. This is also a titanium oxide crystal. And this is a mixture of anatase and rutile, and with small amount of amorphous. And we could isolate anatase and rutile from P25 and check the activity of isolated anatase and rutile. And also we took the action spectrum of isolated anatase and rutile. This is action spectrum for decomposition of acetic acid in aerated aqueous solution. The black line, this is action spectrum original P25. And the anatase, isolated anatase, shows a little bit short wavelength shifted action spectrum because the anatase absorption range is a little bit shorter compared with rutile. And here is rutile action spectrum. And the very important point is P25 behaves at the longer wavelengths as a rutile and at the shorter wavelengths as anatase. So that is maybe your, how to say, in Japanese, itokodori. So anytime in this part, P25 behaves as anode. And in this longer waves range, this behaves as a deuter. So this is very, very active. So this is one possible reason. And another important point is we can deposit a small amount of platinum on the surface of titanium oxide by photoirradiation of titanium oxide suspension in the presence of platinum complex. And this is the action spectrum of hydrogen evolution from methanol, aqueous methanol. And this is the deuter action spectrum, and this is the anatase, isolated anatase. And there is about 30 nanometer shift of action spectrum that correspond, that reflect the difference in the absorption of deuter and anatase crystalline. And the very interesting point is when small amount of platinum is photodeposited on P25, this is black line, this is triangles. This is the 0.28% platinum loaded P25. And this green line is anatase, not platinized, bare anatase with platinum loaded deuter in the almost the same ratio of anatase and deuter. And this point is a little bit different, but almost the same action spectrum is obtained. That means the loading of 0.28% platinum on P25 only produces platinum loaded deuter. Platinum is not deposited on anatase, even though the composition of anatase is about 85%. That means platinum is selectively photodeposited on the surface of deuter. And if we, when we increase the amount of platinum, this black line is a 28% loaded P25, this one. And that coincides with the action spectrum of platinized anatase and platinized deuter in the almost the same ratio. That means at the 28% loading, the anatase particles are also deposited with platinum. So by using this action spectrum analysis, we can differentiate, we can discriminate the position of platinum that cannot be measured, observed by using, for example, SEM or TM. It is almost impossible to differentiate where is the platinum deposit. However, by using this action spectrum, we can easily discriminate the platinized crystalline phase. So, finishing my this is my recent critical review that is published in Chemistry Letters. And at first, this is submitted as a highlight review in this journal. But the editorial committee decided to reject this paper because the title is not so good. So that is preparing articles on photocatalysis. So they rejected this paper because if this is published in Chemistry Letters, this content is, how to say, the willingness that is provided by editorial committee. They don't like to do so. So that is almost rejected, but editor-in-chief, he is very, very kind, and he made a new category in this journal, a personal commentary. I think that every time the commentary is personal, but this is a personal commentary, and that is published. And there is a lot of topics, problems often found in papers in photocatalysis. And also, very, very recently, I wrote a critical review on photocatalysis that is published in Journal of Photochemistry and Photobiology C, Photochemistry Reviews. And this is, the title is Photocatalysis A to Z. And actually, A to Z, the topics starting from activity, band structure, crystallinity to X-ray yield and Z scheme. That is very, very difficult. So for example, Z, how to make a topic of Z, but actually we have a very, very good topic starting from Z scheme photocatalysis. That is two-step photocatalysis. And okay, so this is from A to Z, just A to Z. So if you are interested in my talk, please look for these articles. Thank you very much for your kind attention.